Okay. Thank you for joining in. Last day of the workshop. Yeah, no problem. And okay, so we ended last discussion. Everyone can see the slides and can hear me, right? Online?
Yes, you're good.
Okay, great. So we ended the last workshop by starting to talk about masked language models and running through an implementation, which was very exciting because we actually saw the masked language model in working, right? So we masked a particular word, and with a little bit of programming, we were able to use these large-scale language models in order to fill in the mask and replace that mask with the most ideal, most probabilistically likely replacement token. And so we found that it was like I learned something rather than I mask something. And what we're going to do today is, of course, wrap up that and also talk about sequential language models, which, as you can see on my screen right now, was the other part of it. So again, sequential language models are those language models that are used for things like chat generation or language generation as an extended text generation scheme. Yes, I will be sharing these slides as well later. So whereas the mass language model was used for things like classification, it's usually used for that, or things like just representation learning. What we mean by that is, okay, you have a token, the token has an embedding, we modify that embedding and we learn a new embedding. So that's what representation learning is all about. Representation learning means learning embeddings. And so we already talked about this in the masked language models. Sequential language models work in the same way, where we are still modifying the embeddings, but the key purpose in such a framework is not just to learn representations or to learn tokens inset in the input text, but rather to generate text going forward. So it's more generative, whereas you have a set of tokens now, you're trying to generate tokens going forward. So one thing that you may realize in the setup, these setups are called auto-regressive setups, and they're called auto-regressive because they regress on its own. Like you generate the next token, and then you use that token to generate the token after that. So there is this kind of falling forward approach where once you generate a token, then that token will be used to generate the next token. Think of it this way. If I started in this room alone and a student walks in or a person who wants to attend this workshop walks in, I might adapt my flow, my style of teaching to now the net of all the people in the room. And so if another person comes in, I might modify it further. So there is a falling forward behavior where as and when new words emerge from the sequential language model, successive generations are impacted by these previous generated tokens. And so in this example, I like cats more was the input, and the sequential language model was asked to generate the next token, and it predicted than. Now, what happens is that token than is then added to the input of the sequential language model, and the model is then generating the next token, which in this case turned out to be dogs. So these tokens are generated one after another, and as soon as one token is generated, that token is fed back into the input, and you generate the next token after that. So it's auto-regressive. We call it auto-regressive. Well, it regresses upon its own previous outputs. Auto-regressive is a little complicated as well, because you might think that by the name, regressive means that it's a regression task. But bear in mind that based on our experiments yesterday, you would have remembered that we looked at a probability distribution over 30,000 different tokens at the output. The same thing goes on here. What these language models are doing is based on the context, trying to find the most likely token. Ultimately, it is a classification task across tokens. You have a set of tokens in your vocabulary. Whether you're doing masked language modeling, where you're trying to replace a mask with a token, or given a set of tokens, you're trying to predict the next token, in both cases, your vocabulary is predefined. And it's the model's job to choose the token that is the most likely token, to choose, to classify which among the tokens is the best fit for continuing or insetting the mask that is in the input. So language models are fundamentally classification models at the token level, not a regression model. Yes, question. GPT is a sequential language model because it is generating token after token after token. In fact, the way you can test this out is if you go onto ChatGPT and like paste a very important detail in the top and then ask ChatGPT to say something, and then just take a junk irrelevant news article and paste that like 100 times in chat in the same conversation, and then ask a question about that first fact you entered, you will find that the model, in fact, cannot attend to it because of that limited window size, right? Because as you're generating new tokens, you are forcing the model to shift its attention window. And so the oldest concepts get forgotten, okay? So it rolls forward. It's a falling forward process. There's a window in which it can attend, and beyond that, it forgets.
Adjusted, like when we implement that right here, that is something we can increase the inference.
That is true.
But I think the reason they choose that for the GPT is
Correct. So the longer your window size, the longer the more number of tokens you need to attend to, the more computationally challenging it gets. Because of course, the more pairwise token comparisons we need to make. So the larger the window, the more expensive it is. The window is predefined, and for prompts that are shorter than the max window length or longer than the max window length, there are all sorts of different computational subtleties and tricks that these models use to make the processing more computationally efficient. Okay. Yeah. That's coming next. Yeah. So we just finished talking about the differences in these two models. Now let's see what is one key distinction in sequential language modeling. It's one thing you brought up actually yesterday. It's that, okay, if I just keep picking the next most important token as a classification task, how can I guarantee that after a set number of generations, what I get actually is meaningful or makes sense or is useful to me? Another peer had asked, okay, if I limit the window length to say 50, how can I guarantee that by the time I reach 50 tokens, I can actually end up with a complete sentence and not half of a sentence? So all of these problems emerge from the fact that as I've currently defined it, the sequential language model is only invested in generating the next token. That's it. So you generate one token, you put it in the input, then you generate the next token. However, in practice, this is actually false. The way it is really done is that, we will jump ahead here. We use this thing called beam search. Has anyone heard of Viterbi decoding? Viterbi, I think, was a student at UCLA who came up with, I believe, came up with this algorithm. And we use this idea of Viterbi decoding to look ahead before we take a step right now. So think of it this way. Rather than predicting just the next token, we look at all the possible combinations of the next 5 tokens in series, and we say, okay, Looking ahead 5 tokens, I think I can predict 1 token right now with a higher probability. By looking ahead, ahead 5 or 6 steps, I get a better sense of what I should pick now. If this is not a very familiar concept, think of it this way. When I am playing chess, I don't make a move right now and think of that move as the best move. Rather, I make my move and I think 5 or 6 turns in advance, hoping to get a certain configuration that I know will benefit me. And based on that, I take a move right now. So a similar idea is going on in beam search. Rather than making a single choice right now and then making the next choice after making this choice, I look ahead. I look 5, 6, 7 layers deep or 7 choices deep to figure out which token I should pick now to make the best choice later on. So there is something like a reinforcement learning idea going on here, where I look really far ahead before I make a choice at this moment. Now, you might imagine that the further ahead I look, the more expensive it would become. And that is true. The further ahead I look, the more expensive it does become. So, you know, that's just a fact. And there's nothing you can do about it. There is a trade-off. The further along you want to look before making a decision, the more accurate or the more well-rounded your generation might be, or the more precise your generation might be, but the more expensive it becomes. Yeah.
Like that reduce the computation.
And that's exactly the Viterbi algorithm. So yeah. So they have already thought about those pruning strategies. Because if you think about it, if where I am, I look at the next 5 most likely tokens that I can generate next. But then from each of those 5, I have another 5 for each of those tokens that I can potentially generate. So this number of possibilities, the deeper you go, increases exponentially. Right? So they have ways of pruning that space. They have ways of only looking at like the top 5 most likely paths towards the end of an n-step beam search. But these are not things that we will cover the details of in this class. But they exist. Okay? Another point to make here is very important. So we have already talked about the fact that large language models are doing a classification across the tokens, right? You have a set of tokens. In this example, you have in this first layer here, you have he, great, influence, right? So we have generated some amount of text, and the next tokens that are most likely are he, great, influence. And then from he, if you generate 3 more tokens from each of these tokens being generated, you get influence, had, during. For great, you have during, deal, influence. And for influence, you have and, time, during. So what this is showing you is a 2-step beam search, where from practice, you're finding the top 3 most likely tokens to succeed practice, and you have a probability associated with each one. These were exactly the same probabilities we saw yesterday in the masked language model. So recall that in the masked language model, we saw a vector of length 30,522. This vector was corresponding to the individual probabilities of each token that could best replace the mask in that example. In this example, we are saying, here is my input context, and I'm trying to generate the next token. And these probabilities that you're seeing here are the most likely tokens to follow this practice, this prompt that has ended with practice, right? And so in this case, we're showing you 2 steps of a beam. You have to, at this point you have practice and you're tasked with picking the next token. You can either pick he, great, or influence, right? But what you do first is you say, okay, he, great, influence. Let me go one more step For each of these possibilities, for he, I can go with influence, had, during. For great, I can go with during, deal, influence. I actually run this inference for each of these options to find out what their probabilities are. And then using the total likelihood of both the tokens, I make a step now. So using the fact that he is of high probability and had is of high probability, I can multiply the two probabilities and say, okay, the best path through both the beam steps, he had have the highest, most probable chance of being generated. So for now, I will generate he and then move ahead. Does that make sense? Yeah, this is a fairly common thing to do multiple step generations. This is called Viterbi decoding, Viterbi algorithm. You can Google it. But it's a fairly useful thing in finite state machines. Yeah.
Quick question.
Yeah.
So, can we recall with this flow, with this like two-step process?
Yes.
The calculation that was the flow of the calculation that would go with it, like in with perspective to embeddings.
Yeah.
Like what is happening to embeddings?
Yeah, absolutely. So what's happening is you post the prompt as input into the sequential language model, and you generate outputs for each of the tokens in the prompt. The trick, however, is that in sequential language models, you generate one extra token. That extra token embedding that you learn corresponds to the next token that you have to generate. So whereas you input n tokens, the output of the sequential language model is one shifted. Does that make sense? So for the nth token as input, you generate the n+1th token embedding as the output. That's a very important question, and I don't want to get into the details of how that's done. But the idea is that ultimately you do get a probability distribution across the token space. The most likely tokens that you would like to generate, given a prompt, is what you get as output. And you make a bunch of sequential decisions before you decide right now where to make your next step. So you look ahead. That is the most important thing. Now, I did want to mention one more point, and that is that how do we build creativity into these systems? Now, if I always enter a prompt and I say, okay, look, 10 times out of 10 with this prompt that ends with practice, he is going to have the highest likelihood. I will never, predict great and influence. So how do I get diversity in my sequential language model? How do I get different generations when I am trying ChatGPT with the same prompt over and over again? Any ideas? How do I get different outputs for the same input?
And if now you're higher, like for one of these that I just like say I just gonna go to the other options.
What's your choice?
I would say kind of back out that whatever even search has been made, and if somebody is searching that again, then reshift the somehow the probability.
Yeah. So I think both of you are talking about the same thing. So the idea here is that when you are only looking at the most likely output, a most likely token to follow, this is an exploitation scheme. We exploit the probability distribution and pick the most likely output token. But in addition to exploitation, there's another part called exploration. So at some point, we also want to sample these occasionally, right? You never know. At some point, you may get a very creative output when you sample the low probability parts. So there are many ways they do this. One way is this point known as the temperature parameter. I don't have slides on this because these are all pretty more second order concepts. But the temperature parameter, what it does is very simple. It takes this probability distribution and says, you know what? I don't trust it. I will say that, he is 0.6, great is 0.2, to influence is 0.2. Okay, all of these tokens have their probabilities. I won't trust it. Okay, you say it's 0.6, you know what? I'll give you 0.4. And I'll give the great and influence 0.3, 0.3. So, you say it's 0.6, but who am I to believe you? Temperature corresponds to the fact that when you heat something up, the probability that something is in one point decreases because that point moves around more. So the idea is when you increase the temperature parameter, these probability distributions don't stay like that. They flatten out. So even though the model is suggesting that he has a probability of 0.6, with a high enough temperature, you can suppress that confidence and make it go down to like 0.4. And in the extreme case, you can make them all uniform distribution, where all the tokens are equally likely to be generated. It's a hyperparameter. So they call it a hyperparameter. And anytime you are running sequential language models, you have to set the temperature parameter. You need to set the temperature parameter. You need to set the beam requirements. How far down do you want to look? You want to set the branching factor. How many tokens are you going to consider at every step? The most likely tokens you're going to consider at every step, right? Recall that every time you want to imagine chess. I think the best idea is chess. So you're looking at a board and you want to make a choice, right? There are two things you can do. You can look at the number of moves where you are currently, or you can look how deep a move you make now can affect. So there's something about breadth in searching and depth in searching. I can select from any number of moves right now. That equates to the number of tokens that are available to be selected from. I can decide how deep I want to go in my analysis before I take a step. That results in the depth of a beam search. So beam searches have depth and breadth. Does that make sense? What is the what? The breadth? The number of times you want to look ahead before you make a decision now about what the optimal token generated should be. The breadth, on the other hand, is saying, okay, I'm faced with a board. I can take any number of moves here. It's not just the most likely move. I can take any number of moves. And so for all of these individual moves, I need to think that level deep, right? So for each of these options that I have currently, I need to think 5 layers deep, 5 moves ahead, right? So if at every point I pick 5 options to select, and for each of these I go 2 layers deep, then, or in this case, what I'm showing is I have 3 options to select: key, great, influence, and for each of them I go 2 layers deep. So I go one step, key, great, influence, and I go another step, influence, had, during. It's 2 layers deep.
Oh, okay.
Yeah. Here's another example, right? You can look at on the right side, you can see I was the initial part, and now in this case, you have 5, the width of 5, so you're looking at 5 tokens. Am, will, go, and ... word end, but it's really showing just 5, right? And from each of these 5, once again, you're looking at 5 more. Do you see that? So this kind of search is very expensive. At every point, you consider the branching factor, they call it, but the number of different options right now. And for each of these options, you go all the way down, and then you see what are the resulting permutations that happen, like k layers deep or n layers deep, whatever. And then you come all the way back, and then you make your choice, right? So it's expensive. Okay. Yeah, go ahead.
For the diagram.
Yeah.
You have 5 options.
Yeah.
And each of those options has 3 options.
Well, they're writing the dots here, but it's really 5,
Oh,
right?
okay, yeah.
So
then they have another 4 layers.
so the layers and the branches are separate.
Oh,
So you can go
branches.
any layer deep, but at any point you can explore different moves.
Oh, so you have 2 layers.
Exactly. Yeah, question.
So it's different, different applications.
Uh-huh.
Like
Yeah.
ChatGPT maybe because it's text to text.
Yes.
Right?
Yes.
But for the AI, like I a long time ago,
Uh-huh.
they had the chess champion.
Yeah, the chess champion, yeah.
In that case, I guess you want to reduce the links that the option
Yeah.
to
They were doing both. In the AlphaGo paper that I think you're referring to, AlphaGo 0, they were doing this thing called Monte Carlo tree search, which was actually using, I would say, something very similar to a beam search, and trying to find this value function associated to a particular state, where the state was a board. But we can talk about that application in detail later. But what you're saying is, in precision tasks, how does the beam search get affected versus in creative tasks? So if you want a more creative application, ideally, you don't want to always rely on what the model thinks is the most likely output. At some point, you want to introduce some uncertainty. And so your temperature parameter should be set a little higher. If, on the other hand, you want the same output over and over, set the temperature to 0. And it'll always look at the most likely thing and just go with that.
So for genomics, like we're probably using the experience, but
Mhm. Yes.
I guess for to imputate the data,
Yeah.
you need to use the
Perhaps, yeah. That's a cool idea.
to set the
Perhaps, yes, yes, exactly. That's the kind of intuition, yeah.
when we did the opening
Mhm.
for the hospital, we had to change it up to 7 because at
0.7.
2,
Yeah.
0.7, because at 0.3 it's actually
Yeah, so for some reason they have found that the empirically best temperature for many of these models is 0.7. So why that is, we don't know. That's empirical, and people like to set it to 0.7. So if you want to set it, what's up? I have not. That's the probability. Yeah. Okay, is that straightforward? Okay, that was the only kind of added frill in sequential language models compared to masked language models, that there are all these other generation schemes and tricks that one can use instead of just filling in. That's the usual case of masked language models. Okay, now it's time for solidifying all these concepts with some code. So let's jump into some code. This is from still tutorial day 2. So this is a small part, but it's really not too bad. So I'm here in decoder style models. Are you guys with me? Yeah? Is everyone here? Okay. So before GPT-3 and ChatGPT, I was doing a lot of work with GPT-2, which is the with an inferior version. And so we'll be using that because it's smaller and it fits in all of our free instances with no problem. So again, can anyone tell me now? At this point, I think we should all be conversant. What are these 2 parts doing? Yeah. Yeah, so we are trying to import the tokenizer and the model classes from the transformers library. Okay, so we do that. Just give me a minute. It looks like I haven't run this today. Ran it yesterday. Okay, it's doing stuff. Okay, great. So that runs fine. And now, if you notice again, we take this model name. Again, I'll get to how we get these models. That's the next point. But we load up the tokenizer and the model. So that's the next step. Right? Okay, so it's going to download some stuff. This model is 1.5 gigs. which is bigger than our previous model. So we're going up in size, which is great. GPT-2 medium is the model. Yeah, it's the model and the tokenizer. You cannot run GPT-4 locally. So if you want to run the bigger models like GPT-4, you're going to have to use their API. They host the model. So for patient-sensitive data, you want to run and load your models locally, right? Because you don't want to send your data to their server. So this is safer for your proprietary data because this data isn't going anywhere. All this is running on your compute. Yeah. Okay, so now we do the same thing, right? The cat sat on the, and that's the sentence, that's the prompt, tokenizer.encode. Again, we ran this exact experiment on the first or second day using guidance, but now we're going deeper into the weeds to see how to do it without guidance, right? If you remember. But anyway, so the cat sat on the, so we encode it here. Hopefully we all remember what the tokenizer does, and it returns token identifiers in the vocabulary. Yes. It directly returns a tensor representation of the identifiers. Recall that we used torch tensors as input into the model, right? So rather than having it in a second step, now I'm slowly trying to condense things and make the code more mature in these workflows, okay? So we have two brackets because the first one corresponds to the batch. The second one corresponds to the tokens themselves. You know what? I think it's a good idea to show you what happens in a two batch just for fun. Okay, so let's add another thing here. QC bio is the greatest dot, right? So let's see what it can generate after that. And let's encode this to see what we get. That is not what we wanted to see. So hold on, let me see what's going on here. Tokenizer.encode. The mask is only for the masked language modeling. This is for sequential language modeling. We're trying to generate going forward, right? So I believe we'll have to use a specific command for batches. No, it's not there. Let's see, it's usually one of these. Don't worry about it. We should probably activate truncation or padding. Yeah, so let's not do that because I don't want to talk about those details yet. Let's stick with a single example for now. Okay. So we see what we've used before. So we see the input IDs. This is stuff that we have seen before. So we pass these input IDs, the tensor, into the model, but let me change it back to how it was because I think I had an encode here so that we keep it the same. I don't want to change anything. Is that what we had? No, it does not. We didn't have a list here. Okay, there. So this is what we had. We take a sentence, we encode it. It's a string, and we generate what we've always seen, right? I'm not deviating anything from what we've seen before. Now, the goal here is for the model to generate the next token, a set of tokens. Okay? So now, once again, we just pass the input IDs into the model. And again, given as we discussed earlier, the model will output for you a probability distribution over the entire token space for you to pick the most likely token that follows the input. So the cat sat on we get a probability distribution across the entire vocabulary. And what this line here is going to do is just pick the maximum, argmax, right? Most likely. And then given that index, we are going to decode that index. So as I said, I'm trying to compress stuff now to make you more comfortable with what's going on. Oh, give me a minute here. Let me just import torch for us. Yeah, so 0 corresponds to the first element in the batch, right? As we always are doing. -1 corresponds to the last token in the generation. So whereas in masked language modeling, we are looking for the token represented by mask, in the sequential language model, we look for the last token embedding, because that is the one that contains information about what comes next. Okay?
Sorry.
Yeah.
So 0 is the first element hash, -1
Is the last token. Yeah.
the last.
In the mask, if you recall, our index was 3. I don't know if you remember that around like yesterday. We kept seeing the 3 around. So the difference is that whereas in a masked language model, you're trying to replace the token in the input, somewhere in between the input, embedded in the input, that is denoted by the mask token. In this case, you don't have any mask in the input. You have the half sentence, the cat sat on the. And given that, you want to generate the next token. Think about it this way. This is equivalent to saying that the cat sat on the, and the last element is a mask, right? So if I had mask here, now the same stuff holds. Now basically mask could be the last token in my sentence, and I'm trying to get a probability distribution across the mask to pick the best word that fits in.
If it's not the last
Then you'll have to find out where the mask was. Yeah. Okay, so we did that. We ran this, right? And so let's look at the predicted token floor. So we get the cat sat on the floor. That was one token that was generated by the GPT model. Fair? Did we all get this? Okay.
This is the most likely out of all that you have to distribute.
Absolutely. So now let's see how to add in all the frills, right? This, as your peer just said, if you can't hear on the Zoom call, this is the most likely generated token that follows. But recall that we just discussed things like beam search, temperature parameters. So it might be useful just to quickly go through that to see if we can have some functionality there that makes it easier for us to generate some creative outputs. So here it is. There are many words here that you will not know at the start. So it's under multi-token generation. Okay. So I'll break it down line by line. So there's no problem here. Okay. Model.generate is a, what can I say? It's a way to generate multiple tokens in the evaluation. So model.generate, input IDs, we already know what that is. It's a tensor with the token identifiers. Max length is the maximum length of the generated sequence. How many tokens do you want to generate in the future? Do you want to generate just one, the floor, or do you want to generate many tokens going forward? Number of beams refers to the number of options you pick at any game state. So recall that in a beam search, there are two things. There's the width and there's the depth, right? The number of beams talks about how many different options do I consider right now in my current state as the total number of options to select before I make a choice. So it corresponds more to the width, okay? The width of options to select from right now. Yeah.
Layers.
No. Layers contribute to the depth. How deep can you go? How many autoregressively tokens do you want to generate? Number of beams refers to, okay, at this point, how many different possibilities do I want to consider? Make sense?
So that example, you had 3.
Correct. That would be the number of beams. In this case, we're setting it to 5. And now we can also do things like changing the number of return sequences. What that means is, okay, I don't know if you have seen this in ChatGPT, but recently you will go through and write a prompt, and it'll give you 2 side-by-side outputs and ask you to pick which one is better. I don't if you might have seen it, you may have not. Oh, you're developing that too? Yeah. So the number of return sequences corresponds to that. So how does this work? It just picks the two most likely paths to examine concurrently. Early stopping is true, meaning that if I told you that these models often have a special character that says, okay, if I reach this character, I am done with examining this route further. In chess, if you realize that you've lost the game at a certain point, there's no need to go further from that point. I mean, you've lost, right? So that's what early stopping refers to. Temperature is what, as you have pointed out, it's 0.7, right? So that's the ideal temperature that everyone likes to pick. Do sample reflects the fact, as you pointed out, that if you have a temperature, you want to kind of mitigate the peaks in the probability distribution and encourage the low probability tokens to be picked sometimes. And do sample basically takes this temperature parameter, flattens the distribution across the tokens, and samples one of them given this distribution. So think of it this way. If I have a very high temperature, all the tokens that I can select are equally likely. Basically, I don't trust the model. I say, model seems to think some token is worth 0.6 probability. Who cares, right? What we do instead is we say, okay, so we don't care about that. We have this uniform distribution. And now I will sample, given this distribution, a random token. That's what the do sample equals true means. Irrespective of how much temperature you give, if you don't set do sample to true, all it will do is suppress the max, but it won't enable the model to randomly pick from the distribution. It continues to pick the maximum, even if the maximum isn't that high. So think of it this way. If in my previous example, I had 0.6, 0.2, 0.2, and if I increase the temperature, then this would go down to about maybe 0.4, 0.3, 0.3. If I didn't sample it, I will still pick the maximum, which is heat. But if I say do sample equals true, then you're more likely to see, okay, 0.3, 0.3, 0.4, they're roughly the same. If I sample one at random, with some chance, I will end up getting grade and influence. So having a much larger peak versus a much smaller peak doesn't really make sense unless you're able to sample from that lower peak or more flattened distribution across the tokens. So temperature and do sample go hand in hand. So don't increase the temperature without enabling the sampling process. Yes, question.
Scenarios that you don't want to set one.
In fact, if you set the temperature and set do sample equals false, which is the default implementation, it will throw a warning saying set do sample equals true, otherwise I'm not going to use the temperature. So they go hand in hand. Yeah. So it's more like condition on do sample, you toggle the temperature, not the other way around. Yeah. Okay. So why don't we go and try this out? So again, I was going through it line by line. For now, for the purposes of this workshop, kindly ignore the next 3 tokens. You may not need them. If you do need them, the warning messages will tell you what to do. So these are totally fine. And length penalty basically tells you that if I generate a beam that is too long and too repetitive, then penalize that. So this is another heuristic that's not really that important right now. But what I want to tell you is that many of these different properties, again, they're continuing to add properties every day to this generate function. So if there's another heuristic that helps you select in the beam, then they will add it to it. This is just a start. You may not need all of these even, okay? But there are these options for you to play around with so that when you do actually run this cell, it's going to take a while because it needs to generate many tokens. And then we decode it here, as you can see. And who remembers what the skip special tokens does? What's up? Yeah, exactly. So when you have those special tokens that signify the start of a prompt, the end of a prompt, all these extra special tokens, you usually find them within angled brackets. That's how you know they're special. This skip special tokens will just remove those for you. So let's see what it generated. Again, we just did all this without guidance. Recall that in the first class, we did it with guidance and we didn't really see the depth of what was going on. But now without guidance, you can get the full visibility. We get the cat sat on the floor looking up at the ceiling, and then it just goes on rambling, right? What is it? I don't know. We don't know what it is. I don't know. Yeah, it's language is hard. And even a 1.5 gigs model is only that good, right? What I liked seeing, I guess it's not here. What is it? Yeah, so again, we see the same thing we saw at the start of this workshop, which is that things repeat. At some point, you end up going in a loop, right? So you generate, and then you see these periods emerging, or these repetitions, these cycles emerging. And many people are trying to figure out why such cycles emerge in smaller models. But it's quite interesting. Yeah. Yeah. Those are additional parameters that you can set. I haven't added them here, but you can. They are. If you don't, it will use the default version for you. Yeah. No, they won't. It'll probably set it to like 3 or 5 or something like that. Question.
This is
Yeah. You want to see what happens if we set it to 1?
Yeah.
So 1 is a higher temperature, so we expect more stochasticity. More confusion. We definitely got something different. The cat sat on the floor, his tail wagging in the air. The cat sat on the floor, his tail wagging in the air over and over. Hey, what's up? Hey, what's up? Hey, what's up? What's up? It's a difference. I would say that the cycles are shorter. Like the repeats are happening more frequently. Right? It's repeating over and over more frequently, which I don't know what you want to interpret that as, but it is something. Yeah. 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 So that's part of the special tokens. So what you can do is you can get the model to generate until it reaches a special token. So what we do is in practice, if you have a chat data set on which things are trained, at the end of the chat, you just append a special token during training. So then when the model learns through these chats, it automatically understands that when I reach a special token, I've reached the end of a chat. Or when it generates a special token, we can detect that it has reached the end of a chat. Yes, they are. So what you do is you learn the token vocabulary by examining the training data and finding the most repetitive parts, like we discussed. The example with the versus Roy Chowdhury, where Roy Chowdhury is not really a very familiar span in text, and it's broken up in tokens. We discussed all this. But once you create your vocabulary, you go in post hoc, you add these special tokens in there. That makes sense? It's 1, so it can sample anyway. Yeah. This is only my generation. Yeah. Okay, so this part, the challenge part is not going to be done in the class, but I will be putting this in as the homework for the workshop. So it's straight up copying the code from top, but I think it's very interesting. It goes straight to your point. about what is the difference between encoder and decoder, and it gets you to think about those things. So for the same prompt, I want a piece of, with an encoder model, you would be asked to fill in the mask, which you have the code for. With the decoder style GPT model that we just discussed, you would want to generate the next token with the same input. I don't think that's going to be easy, but I mean, the coding is easy, but I think it'll ask you to think about what these things mean, right? So I'll be sending this over later as a full homework assignment. So don't worry about it. No. We are not doing this now. Okay, so it's a good time to take a 4 to 5 minute break and then resume. We'll start with applications next, after we quickly go through the Hugging Face library, which doesn't make much sense until I start talking about it, but yeah, 5 minute break. Okay, and we're back. And let me make sure I'm sharing everything. Yeah, everyone's seeing everything. Okay, so you might have seen over the last 2 days that we've been taking random names of models and tokenizers and sticking them into code. And many of you asked me, where do you get these models? Well, it's this online repository called Hugging Face. Okay, and Hugging Face, I'm not even joking, has this emoji representing it as its icon. And so, yes, at some point it gets very annoying, and you will only start to see that Hugging Face emoji everywhere. But let's try and go there to see what Hugging Face looks like. This is the Hugging Face website. And this is a place where if you want to get started with using your own open source or using somebody else's open source models, this is a platform and page where you can download people's models. I'm going to walk you through it. A llama model, let's use the one that we talked about, no? So there's all these different models, but there's a big search bar. I'll go with GPT-2 medium because I think we should. Medium. So then we go here and then we maybe pick one of these, right? It says GPT-2 medium, right? This is a model page. That's what they call it. And you see a bunch of things here. There's a lot of information, maybe. You see how many people have downloaded it in the last month. Probably want to pick one that has a high number just because it's trusted. Anyone can post a model up here. So just be careful that you use one that is used by many people. If you want to be sure that this model is good, any model, just go to community and you can interact with folks here to make sure that there aren't any like breaking bugs in the model. And the authors are very fast to respond to you. So it's a nice community. You can interact with people. And the model is described, right? There's a paper associated to it, licenses, right? Explains to you what it does. It hooks you to the paper, the blog posts. Sometimes they even have like an online kind of playground where you can test how it does before you download it, because these models can be fairly big. And then the coolest part for me is that if you just click this button, use in transformers, it tells you how to start off with the tokenizer model. The code is all here. I mean, you would go with this one, not that one, but go with this one, right? And it's there. So you just follow these instructions, you copy paste these terms in your Google Colab, and it'll just directly download it and instantiate a copy of the tokenizer and model in your welcome. So it's very convenient. Okay. And some of them, if we're lucky, also has the code for you to generate inferences. So usually they have two options, one with the pipeline abstraction, which came later, but one with the more rudimentary methods that I've shared in this workshop. So you can usually use one of these. And you'll see much of the familiar code that I've shown you small differences here and there, but you can always play around with it. But usually we are using PyTorch, so always go with the PyTorch one, not the TensorFlow one. Okay, we've been importing Torch in case you haven't realized that. So you'll see stuff like this. Of course, there are parts in this code that you will not understand immediately. For example, you won't understand what the star star means. You won't understand, well, that's pretty much all you won't understand. But for these things, the best choice is to put it into ChatGPT and ask it, what is the star star? And it will tell you what it's doing, okay? That's not the problem. It's actually very easy to get started with these models. Okay? It's so simple.
It's what it is actually is like everybody can post a lot of models at one place.
Models, data sets, it's a big resource. Yeah. Okay, huge. I can't overstate it. Everybody starts from here to do NLP or vision now. So let's see, even the latest models like cutting edge are all here, like Gemma from Google is here. It just came out. It's the Google's version of Llama 7B that they say beats Llama 7B, but no, I don't know. But the papers claims they do. So sometimes you'll have to acknowledge a license, but you'll get the same information. Again, always just click this button, get the instructions, and get going. Yeah, pretty much all these models are free. Sometimes you have to sign licenses. So in the licensing, you might find some issues, but there are many open source options. Yeah, absolutely. Makes sense? Okay. So that's where I got our checkpoints from, in case you're wondering. And so usually you just specify this path like you saw in the code, like you will continue to see. But yeah, makes sense. Okay, so I was excited about this, and so using the same process, I went and said, okay, do something with DNA, because wanted to make it somewhat relevant. And I ended up finding this one really nice model that I want to share with you. Right, so I found this just by going through it. Of course, it doesn't have many downloads, but I played around with several to find this one that was quite interesting, right? And this one, again, it gave me all the instructions to run inference, so it wasn't hard, right? Oh, it's all there. They give you the code to run the model, so you don't really have to do much. Yeah, that's really how simple things are. So now let's jump to tutorial day 3. I'll show you. Let me see. So again, this is not code that you're familiar with, but this is code I pasted straight from the web page. Okay. I can explain to you what goes on in due time, but what this does is that let's try and run it. We just found some code. We want to play around with it. The model on the web page looked exciting. So we want to play around. We go onto a Colab, we copy paste the code, and we try we just try an output as they recommend in the web page, right? I'm not doing anything here that's particularly mine. I'm not developing anything. Okay.
You wrote that sentence?
I wrote that sentence. Well, that doesn't sound like something I could come up with, but I probably found that sentence too. Yeah, let's wait for it to do its magic. So again, the model page would tell you what it does, but we want to test it out for ourselves, right? Things are downloading. Hopefully you are also working through this part. Yes, I'll be there. I'll be right there. Yeah. Yeah. Yeah, it's stored in vocabulary JSON and tokenized objects. Yeah, and even merge stuff next. They all have it. So the way the tokenizer is built, just for your benefit, you create the smaller words first, and then you start merging them together. You might have heard of, I think it's very similar to some kind of hashing method, where they keep grouping words that occur together into another subset, and then they add that to the dictionary, and then it's some kind of aggregative approach like that. You might have heard of agglomerative clustering. Yeah, similar mentality goes on here. Okay, so what does this model do? Can anyone explain to me just by running it blindly? Yeah, so it takes in a sentence, right? That's pretty heavy for me to understand. Okay, like there's nothing here that makes sense to me. And what it can do, just off the bat, we'll get into a more detailed use case soon, is first of all, take a span in the sentence, classify it as one of many entities. That is, okay, we're talking about a protein. It even gives you a confidence score on how sure it is, and gives you the starting and ending character in this long sentence from which it picked this out. So 35 would be the 35th character from the start. If you count 35th character, you'll end up at 1. These are all just examples of models that you can download and just run like this and try to figure out what it's doing. Question. I see a confused face. Yeah, so I was going to ask you, what kind of model, first of all, do you think this is? Is it an encoder style model or a decoder style model? Is it a masked language modeling type task where you're trying to fill in? Things are all about filling in. Or is it a more generative, creative task where you're trying to do sequential language modeling going ahead? Which one is it? Yeah, so it's the first one, right? So it's an encoder style model. And the giveaway is that, of course, you're not generating new text that follows. It's not really used for a creative task. Rather, what you're trying to use it for is, given a set of tokens that is in this input, you're trying to classify groups of tokens as belonging to a particular entity. So if you were to come up with a model architecture of the encoder style that accomplishes this, can you try to brainstorm with me ways in which you would do that? So recall that the encoder style model has a mask in the input, and it tries to predict that mask likelihood in the output based on a probability distribution across the vocabulary. Now, in this case, I want to use the same architecture, but I want to repurpose it for a classification task where I classify specific spans into different types of entities. If you feel kind of lost, that's kind of the point, because if you have a new model, you will also be wondering the same things, right? So what do we know? We know that given a prompt, any model breaks it up into tokens, right? So it consists of 25 exons, maybe encode, ing, 1278, we don't know how these tokens are being split, but they're being split. And now, what do? It goes to the encoder model. All of them have to do that. And each token's embedding gets modified to a different embedding. So now every token here has a contextualized embedding reflective of the context from which it came. So if you are given token level embeddings. How do you want to use it to build a classification task? You can be radical. I mean, there's no right answer here.
Just classify ones. Yes. Seconds.
So we want to classify along the entity groups, right? Protein, gene, this, that, things like that. Uh-huh.
And find the ones most similar to it, or put together.
So how would we do that at the token level? How would we group words? How would we reconstruct this? How would we get a span corresponding to anything? What might you guess? So let me tell you how it is done, and you'll think that it's pretty obvious after I mention it. What is done is every token is first classified into one of three things. Okay? So for example, if I take a token, okay, this token would be classified into start of a span, of an important span, middle of an important span, or the end of an important span. Span is a text span, right? Like a text phrase, if you will. So every token is classified into one of three things. So if I had a sentence like this with multiple tokens, again, we have to start thinking about things in terms of tokens, right? So 1278 amino acid glycoprotein. Now, if you had a token 1, that would be classified as beginning a span. 278, the token embedding for that, would be classified as continuing a span. How would it be classified? We train a model. We take our token embeddings, we pass them into a secondary model, a simple, maybe even an SVM could do, maybe a neural network could do, something that takes the individual tokens and classifies them as either beginning a span, ending a span, or middling a span. Once we get that, we basically have an idea of the critical spans in the input text segment as a set of words. So you see how by creating this beginning, end, and middle, we are able to construct sequences, contiguous sequences of tokens that are important. That is the first step. Does that make sense?
Why don't you just have like a set of, because what would it have is in regular NLP is it would say it would be labeled as protein, gene, auto, these tokens.
It depends, right? You can solve it in many ways, but the point of this is to show you that there are two things required. The first thing is to do a span identification, which is to tell you that, okay, this contiguous set of tokens, Ti to Tj, is corresponding to one entity. That is the first step. What entity it is, that comes next. So it's really a two-step process. The first part is to use the individual token embeddings that are contextualized and individually classifying them as the start, middle, or end of something important. Your question?
Yeah, can multiple spans overlap, or are they discrete?
So all that after that has to do with heuristics. So that's model specific, how they fix that kind of overlapping issue. But that's an important question that has to be answered. So if I get now sets or sequences, subsequences of tokens that exist together as being important, think of it this way. We are having this workshop, and maybe people to the right of me learn something different than people to the left of me. Okay, so we each have our own token embeddings. We are each holding a beginning, middle, or end of the group that we're in. So we're all forming B lines, and one of us is in the beginning, one of us is in the end, the others are in the middle. Now, what we want to say is that, okay, this group constitutes a protein, and this group on the right constitutes a gene. How do you propose we do this with our individual token embeddings on this side? Take a guess, there's no answer. That's true, but we want a model to be able to learn that. We want a model to be able to say, okay, given this group with these embeddings, that corresponds to a protein. Oh, the what?
Funding that. Say in the higher space, I think they come together and it's also.
So you did say something very important. You said they come together. So what can be done is that if you have multiple tokens that form this phrase in one span, that form this phrase 1278 amino acid glycoprotein, that form one group, and you want to classify that as one thing, then what can you do? Well, you can take the embeddings of each of the tokens corresponding to each of the tokens here and just average it. Average all of your embeddings to form one embedding and just train a classifier to figure out which entity that belongs to. The point in this is all very simple in case it's overwhelming. Token embeddings contain contextual information after they have gone through the encoder model. And you can use those embeddings in very powerful ways. You can take the mean of the embeddings and say, okay, this is the representation of the input. You can concatenate it, say something else. You can individually classify the tokens to find spans. You can, find embeddings that are off to the side and say, okay, this is noise. Token embeddings have all the information about how that token corresponds to the other tokens, right? So that you can do token level classification where individual tokens are classified as one or the other. You can do span level classification where you first find the tokens that exist together, take the mean, represent that span as one embedding, use that as a representative vector for the entire sequence. So if I gave you a sentence, and this is important, if I gave you two sentences, I like apples versus I want to work at Apple, if you pass both those inputs into an encoder style model, get the embeddings out for each of the tokens and take the mean of all those embeddings, you will get different embeddings. Why? Because the apple in the first case is attending to the word eating. The apple embedding that initially started off at the input of the encoder model as the same token moved to one side because of the eat token. In the second option, the same apple embedding, because of the word work, moved to another side. So when I take the average of all the tokens after they have been attended to in an encoder style model, you get two different representations. And so that is how many assistants today are able to distinguish which entity you're actually referring to. And this is called entity disambiguation. It's a very important task. And so there's so many such use cases. And I just wanted us to start thinking about how token level features can be used to do much more powerful things at the phrase level. Make sense? Have we started thinking about it? Okay. We'll get into a more detailed use case very soon. Yeah.
12, 7, 8,
Yeah.
last, and that's each one of that is a token.
Yeah.
That combines those tokens together.
Yeah.
And then how does this?
Well, we just train another model. We get a vector, we train it to predict protein. Another SVM, another logistic regression, logistic classifier, right? Another model. Exactly. Well, and a different average. The point is only that the token embeddings have enough contextual features for you to do any downstream task using any other model that comes later. Recall that these models are not merely taking just the tokens, but rather the tokens attend to one another within the encoder framework. And as a result, a single token is aware after it has gone through the entire encoder model what the tokens are around it. Yeah. Yeah.
If that phrase had one,
Yeah, go ahead.
that phrase had 1550, that's
Yeah.
something, then the embeddings or the mean of the embeddings would be a different representation.
Yeah, that's exactly right. The mean of the embeddings could potentially correspond to a different context because that's what it's trying to do.
Right.
It's trying to do pairwise token comparisons.
And then what happens after that?
Well, then you're done. You get the token embeddings after the pairwise comparisons. And then this now embedding for a particular token is aware of its surroundings because it's been doing that comparison for a while now. And so individual token embeddings can then be classified. You can group multiple embeddings together. You can take their average, say, okay, what is this new embedding looking like? You can use it in many creative ways.
And then for this specific example,
Mhm.
it's being assigned to something called.
Correct. Yeah, exactly. Yeah.
So if, there are different ways, as you said, to represent these embeddings.
Yeah.
So is there a way that a user can force it, like, okay, I want, the model, consider the mean of this span and stuff like that, so that embedding representation works accordingly, or?
Yeah, so there are ways. You can start by looking up Siamese networks. SIAMESE, Siamese networks.
Thank you.
Yeah, no problem. Okay. We're not getting into that. Okay. Well, we might in a way. So let's get into one more particular and detailed deep dive into one application, and that would be the last thing that we do in this workshop, okay? Followed by an important quiz, which is going to be super easy, but don't worry about it. Okay. So as I was saying, and I think we've all kind of come to the conclusion that it's easier to construct representation learning models, at least as a first step for genomics applications. I mean, if you had a genome with ATGC characters, having a decoder style model to auto-regressively generate new values of ATGC is actually, I don't know if I can think of an immediate use case, but the experts in this room might. What we try to do is say this. Now, if I am given a long genome, can I use encoder style representations to do sequence alignment? Okay, so that's the topic of this use case, which is sequence alignment using transformer models. Okay, so we've already talked about all this. And so one of the most important things before we get started on how to do that is just to recap that one of the motivations that we built to a lot of pain is that given an input sentence, it's broken up into tokens. Each of the tokens are embedded. Language model takes these embeddings, modifies them, right? And we call this pooling. Basically, pooling means average. We take the average and we can basically compress, or we can just take the average across all these embeddings and we can generate one representation that is representative of the entire text segment. We have motivated this. There's no problem here.
You choose one.
We don't choose one, we average across the entire set of embeddings after it has gone through the language model. Clear so far? So what we essentially have now is a sequence level representation, numerical representation. We take in a random sentence prompt, we pass it into the model, we get the modified embeddings, we collapse them, and we get one vector that represents the sequence. Now, one thing that you might immediately be thinking is, okay, if I want to do sequence alignment, what is the primitive task? The primitive task is, I have a read. Read is basically a small sequence of, I'm going to simplify it quite a bit, of say about 100 to 200 bases. And I'm trying to find the exact location in a much larger reference genome of like 3 billion bases where this read is positioned. That's the simplest setup. And so how do we go about trying to attempt this using transformer models? That is the problem setup. Okay.
You created this, you have an average, and now you have,
Mhm.
you're gonna take it to the.
We have a person attempting the solution directly, and I'm very excited about it. Please, yeah.
Oh.
No, please go ahead. Yeah.
Okay, so you're gonna read it 200.
Okay.
You're gonna find those 200 in an actual DNS.
True. Yeah. That's the question. But how do we do it, right? Because that's tricky. See, if you might think, oh, we'll just put the entire reference into a transformer model and then do something, not quite clear, because 3 billion characters do not fit into a transformer model directly. It's just too many bases and not quite clear what we're going to do with that entire reference, even if we did get it through a big language model. So yeah, so it's actually a tricky problem, right? What do we know that we can do? So given a short sequence of bases, what this transformer model types can give us is a representation of that sequence. If I get a read of 100 to 200 bases as the input, then my language model can generate one representation of the entire read. If I have ATGC, whatever, right? You can tokenize it, you can embed it using a custom tokenizer, and then get the embeddings. You can make it go through a language model, and then you can pool all these different embeddings together and get one numerical representation of this sequence. That's something you can do. That's what you have at your disposal. But the moment you go to like 10,000, 100,000, million bases, and then try to encode it, first of all, it's computationally very expensive, all at the same time. Second of all, when you average across too many tokens, somehow you end up just going to a mean value of whatever you're trying to represent. So it's not really that useful. Shorter contexts with fewer tokens that rely on one another more effectively, it's better to have representations for the shortest piece of text that is needed for you. So again, we haven't yet talked about the solution. We're just trying to build questions about why this is a challenging task. Okay. What is sequence alignment done for? Any experts who want to take this? What is sequence alignment done for?
Sure, I can take it.
Oh, we have someone on Zoom.
Yeah. Let's see if I can turn my video on. So sequence alignment is typically done to look for changes in disease. So for example, let's say we have the normal sequence, which is, let's say, 3 billion base pairs. And then you take a disease, maybe a cancer, sequence that. So there is going to be changes. So how do you find that? So what you're getting from sequencing, when you send DNA for sequencing is a bunch of strings, each one is, let's say, 150 bases long. Now you have to match that to the 3 billion base pairs and find out where it came from. Now, if the match is pretty good, you have only like 1 or 2 errors, which are, mutations, then it is easy. But if the match is not very good, like for example, out of that 150 base pairs, maybe 50 of them is missing. So then there is a lot of trouble with trying to find where it matched, because now you have to match the gap as well. So what is typically done in DNA sequencing is you take the whole 3 billion and then divide it into chunks, which are called seeds, and then generate a hash from that seed, which will be like, similar to what Pawan just said. You create a number for that, and then you do that for the whole genome, save it in memory, and then when you get your first sequence, you create a hash from it and try to match the hashes. This is how typically DNA sequence alignment works.
Thank you.
Right.
So let's continue from there. It's a perfect segue into the solution. Yes, but let's keep going. So this uses, as you can see, DNA and transformers. And so I thought we'd end with the use case that's sort of related to one of my projects. Okay. So this is all a lot, but let's start with how we do it. Okay, I think we have all the different parts where we can explain this fairly clearly. So the peer just mentioned that we break up the full genome into smaller chunks, which here we will call fragments or the long context. Okay, so these long contexts in our use case went up to 2000 lengths. So if you can imagine, in a 3 billion genome length, if you have a long context of 1,000, you will have 3 million such long contexts. Okay, does that make sense so far? Yeah, we divide it up. Now, what we do is we pass these long contexts into an encoder model. Are you with me so far? Every long context gets a vector for the long context. We're still okay? Okay. Along with the long context, here comes the trick. We also identify a much shorter 150 to 200 length simulated read that is said to come, and we know for a fact, is said to come from this long context. This is during training. So we have full control over where the read, the simulated read, and the chunk or the fragment or the long context is coming from. So during training, we say, okay, I will take a chunk or a long context of length 1,000. I will subsample a small little sequence within it, and we'll call that the read. And that's what I represent here as short, okay? So that's the short sequence, which is typically the read. And so for the short sequence, we pass it again through our encoder model and get a corresponding vector. Okay? Are we clear so far?
So you break up the genomes into chunks.
Yes.
Call them the long context.
Yeah.
Pass long context to the model. And then the model gives you one vector.
For each fragment. Yeah.
And then sample small sequence of the
Correct.
and you call it short.
Yeah, we call that short. That's all we've talked about so far. Yeah, because we haven't talked about anything. Okay, so we have a short subsequence within the long context that goes through our encoder model, and we generate a vector for the short for the short a sequence, a read.
Two.
We have two vectors. That's exactly right. So we have a vector for the long context and a vector for the short context. Now, where the innovation comes in is that we train this AI model to make it such that if the short context did indeed come from a particular long context, then the vectors are closer to one another. If this read does not come from the same long context or chunk, then these vectors have to be far away from each other. Yeah, question. Yes.
Are there any talks between?
Yes, there are cross versions as well. So in a certain training step, you find like 4 to 5 chunks or fragments, and within each fragment, you find one small little random subsequence, and you call that a read. So we get fragment read pairs. We are guaranteed that a particular read comes from its corresponding fragment, right? Because that's how we got the data. But at the same time, we also know, because we're looking at 5 or 6 contexts at the same time, we know that if I got a read from the first long context, then it could have also come, well, in very rare occasion, would it also come from another long context? So a particular short read comes from a particular fragment or long context. Are we clear about that? But that read, by the definition of how, by the extent of the repeats and the frequencies of how they appear in the genome, is highly unlikely to be a direct subsequence of other fragments, of other chunks within our training step. Okay, that's the trick here. Questions so far?
Put it in a way like a short, where it belongs to the long context.
Yeah.
One,
Yeah,
not be one.
correct. We do that. Well, we impose that. So we say that these long context and short pairs that we know are one subsequence within the other, we call these positive samples. And the ones that are cross, we call those negative samples. Okay? That's where we are so far. What do we do with this? Well, we train this AI model. And what this model learns is to say, okay, if I have a fragment in one direction, now remember, we're creating vectors corresponding to the long contexts and vectors corresponding to the short contexts. That's our goal. It is the same model that is encoding both the short and the long contexts. So what this model will do is that if I am given a pair of a fragment and a read within it, the model learns to generate 2 embeddings that are close to one another in a representation space. Okay? Are we clear with this setup?
Closure the embedding, then it's more likely that the lead came
From that fragment. That's exactly the motivation here. So your peer just said that if a read is closer to a fragment or a chunk in the embedding space, then it is more likely to have come from that fragment. So if I take a particular read and say at some point I'm comparing that read to 5 different fragments in the embedding space, the fragment closest to that read in the embedding space corresponds to the fragment from which that read came. That is the motivation for this sequence alignment using transformer models, okay? So we take the long context after training the model now, and we put all the long context representations into a big store. This thing is called a vector store. We store all the fragment embeddings, all the 1000-level long contexts into an embedding space. And you can Google these embedding spaces. These are called Pinecone, for example, is a very famous up-and-coming vector store that people like to use these days. The idea is now that 1000 length chunks are being mapped by this trained AI model into a space. Okay. So think of these points as anchors. Okay. So I am initializing a party, on say frat row, and all these blue points are people who have been invited to the party. I am not yet there. I will be a read. Okay. So I come in with my own short little read. Fragments are there in the store. People are there at the party. I take the short read. I use the same model. I create a vector for the short read, which I can do. I've trained the model already. The trick here is that now I go into the party and I try to find the people I know at the party who I'm most familiar with. These blue points refer to the fragments or the chunks from which this particular read is most likely to be derived from. So we can significantly reduce the search space in the genome by limiting the search to those fragments that are closest to a new read that we discovered in the embedding space. Is it?
It'd be much faster than traditional way of mapping. Sounds like.
Well, what I will say is that it's much faster than the very traditional way of mapping, like by using something called the Smith-Waterman distance, or which is basically edit distance. I don't know if you've heard of it. But if we compare this model to methods like bowtie or much faster BWA MAM2, these are all much, much faster. They're written in C, C++, highly optimized across CPUs, GPUs. So we're not quite there yet. So what I want to show you is one interesting use case where such a model works, but not necessarily that it's currently be state of the art, but it really comes quite close.
One question about like maybe more details you would have something. So
Okay.
regarding some cases,
Yes.
because like the rays also have the captures, right?
The what?
The what's it called, the DNA sequence.
That's right.
You have the barcode.
The special tokens.
Yeah,
Yeah.
the barcode. So
Yeah.
so usually the way we do is we multiplex
Okay.
based on barcode. to
Oh,
format
I see.
signals. Wondering, like, what does this do with that?
That's a very hard question for me to answer.
Maybe more relevant question.
Yeah.
Like, in the sequencing, you have arrows.
Errors, yeah.
Like you have the A to T or whatever.
Yeah.
And I wonder how well this deal with that.
Yeah.
Versus the traditional like word bottom two.
Yeah. So we have found that we are not bad in dealing with errors. We did a comparison to bowtie too. And currently across all metrics, we're slightly worse. But I think we're getting there with the next, bowtie, these models have been developed over decades. And I think that with a little more improvements to this current architecture, we can definitely get there. But more than that, I think what is more cool is that because of the way we're doing this with taking an embedding for a longer chunk and a read and trying to say that they are close to one another, it results in some very interesting artifacts in the embedding space. So here's an example for you. When you take the embeddings for the long context and pass them into a lower dimensional space to view, like a T-SNE or a UMAP projection, you notice something very interesting. You notice that, in fact, the fragments that are ordered in the genome similarly form a manifold in the high dimensional space, in the 768 dimensional space, which is a little more complex to understand, but it goes to show that this idea of trying to solve sequence alignment has resulted in methods that can potentially implicate solutions for genome assembly. So, but I don't want to get into that. Let's stick with sequence alignment for now, and just talk about how you will implement it now with some code, because you'll be implementing a very simple version of this. Yeah, clarification. Why do we need to set up a store? Yes, because when I am a new read walking into a party, I cannot find the fragment closest to me if I don't have those fragments already there. That is the place where I'm storing all my fragment embeddings. And the key really technical development over the last 1 to 2 years has been that these vectors in a vector store can be accessed very fast. They have really created some miracles with vector databases and vector search stores. And imagine, right, we have 3 million vectors of 768 dimensions in this vector space. Every representation, every token embedding is 768 dimension. When you pool it, take the average, that's also 768 dimension. And so we have 3 million such embeddings, 768 dimensional representations in a vector space. And somehow in a matter of milliseconds, and with log complexity scaling, you're able to take a new read and code it into a new 768 dimensional vector, and in this continuous space, find the nearest points. That, I think, is the biggest technical advancement in this space that really helps build these kinds of models.
So without it, we cannot just.
You will be doing it without it, but it's going to be a much smaller thing. But you can. There are some open source versions that have been developed for many years, but it's hard, right? Because if you had to do it without a vector store, what would you have to do? You're a read. You'd have to go to every single person at the party and ask, am I close to you? Am I close to you? One at a time. That takes way too long. So they have some really nice approximations that they do to find the k nearest fragments to you, or the k nearest people to you at a party.
So then for the second slide, I'm sorry, not the second, the next one.
Yeah.
The one with, yeah, that one. So that one you put it together. So yeah, this is all of the vectors.
These are all the people at the party. And what we find is that, recall that these people are actually fragments or chunks that come from, that are ordered along a genome, right? So chunk 1, chunk 2, chunk 3, all the way up to 3 million chunks. When you project our embeddings into a low dimensional space, you find that similarly they create a sequence in the low dimensional space. So you see these really nice looking trajectories. The fragments, yeah. Fragments and the reads, but mainly what you're seeing here are the fragments. Yeah. And that's pretty cool, right? Yes.
Do you respond like with single cell using cluster, so they cluster together, but this form a line?
Yes, it forms a line.
I guess it's interesting because I try to understand I don't quite get why.
Because, yeah, I can give you some insight into that. If everything was in a cluster, if all the fragments were at a single point, then for a new read coming in, it wouldn't be able to differentiate which fragment is closest to, because all the fragments would be equidistant to it. Right? So you need to have some kind of separation in the fragment embeddings. And so the way you would do that is because essentially this model that's been trained is able to look at subsequences, like you have a long chunk and a read, and is able to tell you that this read is within this fragment. If you imagine one fragment and one read at the end, these two vectors have to be aligned. If you imagine another fragment with that same read at the beginning, these two vectors have to be aligned. So it implies that these two longer chunk embeddings are also, they get closer to one another. So that's a little intuition there.
Oh, so the longer chunks, that's what the smaller.
Yeah, they're both represented here. Yes, question.
So when you test your model, when you use your model, So what do you do if you have a read that have no exact match? So
Yeah, so the way it's done is we just provide the best top K candidates as the matches. Of course, if there's any noise, as your peer just mentioned about how there can be one or two indels, in that case, then you won't find, there might be a chance you won't find a perfect or exact match to the genome, but you can find a very good match in terms of the Smith-Waterman distances. So basically what we do is in the vector space, we don't just find the closest fragment, we find the top 50 nearest fragments. So we can give you a probabilistic sense of which fragment is most likely to contain your read.
I'm saying is that if you have a disease,
Uh-huh.
fragment doesn't belong, that's the part.
Well, the read is coming from, as far as I get it, from a specimen that has the disease, but the original genome reference is disease, ideally disease-free, right? Without those same changes being expressed. And so when I'm trying to compare this read to the genome, of course, I will not find a perfect match, but I'll find an approximate match. And where I think bow tie, Smith-Waterman distance, all these different methods, BWMM, Minimap, all these models differentiate is what they consider to be the best or the highest quality match to the reference genome. We have our own different estimates of what that is. Yeah, so I think that's kind of what's going on here.
We have every time sequence are Wi-Fi, there is a lot of SNPs, like we use, like, but not SNPs, or I should call it SNPs, but like mutations.
Okay.
So, already deviated from that.
Yeah.
Like, I think we have, like, I'm working on that's.
Uh-huh.
I assume
Okay. Yeah, I mean, we did a side-by-side analysis to Bowtie, and we found that Bowtie just beat us out of the water on most benchmarks. Yeah. Yeah.
So, you mean, what does it?
No, why does it mean?
So in Gmail, there is always like limitation because, I guess, just to simplify it, you can understand is that a random process with DNA replicate the image status during replications, where when DNA break, that something try to fix it, introduce it. So, because the reference genome sequence a long time ago, like for us, and you're taking the population from that and fully bred that for bad conditions, even though you're not introducing selection pressure, so you're allowing this mutation to accumulate for like years, and now you end up with a genome that is already different because of the accumulation of the mutation. With a genome that is different than the reference genome.
Yeah, question.
yeah, so some part of the genome
Uh-huh.
are very complex, some part like macro align, and the other part are relatively easy.
Okay.
So do you see a different performance in your model depending on where the genome you're?
We tried a few things. So we did try training on chromosome 2 and testing the alignment on chromosome 3 or Y, and it does really well. We tried training on chromosome 2 and testing it on rats, and it does really well. So it goes across species to, I believe, yeah, even bacteria, rat, monkeys, all the performances are pretty high. Yeah. Uh-huh.
There are some regions,
Uh-huh.
repetitive regions that are super repetitive.
Okay,
Like responded to because
I see. Okay. See, that's very interesting. We should talk about the project later. Yeah, absolutely. Okay, before we review, let's go back to the code and let's do your last challenge for today. I hope that this will take about 20, 30 minutes, that's it. And then it's pretty much coasting after that. Do you guys want a break? Maybe I should give you a break. Okay, 3-4 minutes break. Okay, we will take a break. Okay, so the way this is going to go is there are, so there's just a couple parts that I'm going to introduce you to. I won't tell you what it's doing, but I want you to figure out what this mystery code does. Okay, so there's some mystery code at the end, and I want you to take some time and figure that out. Make sense? Okay. So we will run this as usual. So we found a DNA BERT baseline. So this BERT model on Hugging Face was trained on DNA sequences. The tokenizers are only trained on ATGC. Everything is ATGC, okay? And it's 117 million parameters, DNA BERT2. And I'm sure you'll still see some things that you don't recognize. For example, trust remote code. Sometimes you'll require that when the model has to self-download from the cloud, you'll have to just add that so that your computer doesn't think it's a virus or something. Okay. INOPS was just something that they recommended. I install. I have no idea what that does, but it's basically, I think, short for Einstein operations. What? Oh, you do? Well, pip install is fine, but the INOPS package, I haven't really used that one. Yeah. Okay. So now I will run this. So this one is basically going to output a set of what we will consider for now to be our quote unquote fragments. Okay. These are randomly generated fragments. And I've generated 50. You can increase it to 100, up to you. 1,000, that's fine too. Okay. But I've generated 50 fragments here, and we're going to use very small numbers. So this is how big are these? These are of length 30. So in the use case I just explained, we use 1,000. It's not. This is just a very carefully curated test bench for you to try a very similar use case. Yeah. I don't want to give away too much because the challenge is to figure out exactly what's going on. So don't worry about it though. Okay, so then we go here and we do something here, magic beans. Okay. So finally, here's some mystery code, right? And let me just make a little bit of ease for you. But actually, let's leave it like this. Okay, so then I run this. And then I run this. Yeah, and I get some values. And okay, take your time, 5-10 minutes, maybe 15. Try and figure out what this code is doing. Nobody shout the answer. Well. One second, I'll come in. Yeah. Yeah. So don't feel shy of adding print statements. See what happens, right? Get into the code, break it. If you break it, just download another copy from your email. There's of course some code here that you don't that I haven't shown you before. So try to figure out what it does. Take your best guess. You can even change this value here to verify if you're right. You can feel free to change that. I thought it was fitting that this whole mystery code is brought to you by ChatGPT. So they generated this last challenge for you. We have a hunch of what's going on. Yeah. Yeah. So that's absolutely right. So let me walk through it. Yeah, question.
The protein amino acid that they encode as
In this example?
DNA.
Yeah, I don't know what it's learned, but yeah. But yeah, I could be. But let me get into the computational aspect. So what we did here is that we generated 50 fragments of length 30. And we got a vector that's of dimension 50 cross 12 cross 768. What is 12 here? Anyone? What's 12? The tokens, the number of tokens, right? So you have the number of tokens here, and each token has dimension 768. Then here, as I described previously, we do a pooling strategy where we take the average of all the tokens corresponding to every fragment. And so for every fragment of the 50, we get one mean embedding of the fragment, of the chunk. It's a 50 by 768 matrix. Okay, so far so good. Now the mystery function takes in a read, and we get the output. We generate the read representation, which it turns out is a single read, so this mean actually does nothing. The cosine similarity part computes the cosine similarity between the embeddings of the read compared to every single fragment among the 50. We get a certain cosine similarity set of values. This sorts them in reverse order so that, a cosine similarity score of 1 basically means that the angle is 0, so they are aligned, right? So you inverse sort them, and then you reproduce the fragments corresponding to any read. So let's take a shorter read that it thinks are close to this, to the individual fragments. You might say that the performance is not very good, that, okay, in the embedding space, all these vectors seem to be nearly equally aligned with this read. And you would be right. This is why we trained the model that we did for our research, because these existing models cannot do this kind of a computation. But if we replace this model with ours, it can do this in no time. Does that make sense? Yeah. So you are a read, and you're going to a party, and the way you figure out if you're similar to a fragment is to compare the embedding's cosine similarities. Okay? If the vectors are aligned, cosine 0 is 1. So those values would be high. So the closer you are to a fragment in cosine space, the larger the cosine similarity. Okay? So that's what we did in the arc sort. The 0, once again, I believe has to do with the first batch, but it didn't work without it, so I just put it in there. That's the way most of these things work, by the way. So the -5 says, I first sort it straight from smallest to largest. The -5 colon says, I take the last 5 values. The colon -1 says, I rotate it. I just rotate it from, you know, yeah. I reverse it. Pretty cool, right? Okay, so with that, I think we have reached the end of all the material I wanted to cover. So the first thing Eloy has enforced me to do this is to review this workshop by taking a QR code, and please provide constructive criticisms about the workshop and what you want to improve. We will be offering this again next quarter, and we will take your reviews very seriously. So please go ahead and do it. I'll give you like 5-10 minutes right now for that. And then we will have the quiz. I hope the QR code works. I think it should. Right?
And you're getting the mean from the
That's right, exactly.
and then it's stored.
Access it for cosine similarity. Yeah. Yeah.
For this example, I wonder how the token works.
You should actually check that out. It's quite interesting. I believe it breaks it up into k-mers.
Okay, I see.
But it depends on the model exactly. Some of the models I saw earlier broke it up into k-mers, like 4 or 5.
Tamers are the overlap, right? Like
From a computational perspective, all I know is that it breaks up into 5 or 6 sets.
because in sequencing alignment, the tamers are overlap.
Okay.
Like different, like it's like a slide.
I see.
This one and then different by one base pair, like stacked.
I see. No, then maybe I misspoke. But it's, I think, 4 to 5 spaces together forms.
I see. Okay.
Makes kind of some sense, right? Because if you look at the number of tokens versus the length. Yeah.
Thank you.
Yeah. I don't know how long the survey is, so let me know if it's short enough, then I can move on, right? So take your time.
It's probably with cookies.
That seems to be a problem with, I think, your phone settings. Key is usually a phone-related thing. I think I can temporarily pause it. I'll let it go. Not working. No.
Sent it to my phone. I mean, I sent it to myself and then I
Is it not working for others? It's working. You managed to send it? You sent it to your laptop?
yeah,
Okay.
it works now.
Oh, it works?
Yes.
Okay, it works. Okay. Maybe you can try refreshing. Yeah. Oh, okay, okay, okay. I will move to the next slide so that you can do the next thing in this. Okay, so once you're done with that, here's a link to a quiz. It's my first time using Kahoot. So it's a place where you can host quizzes. So kindly, actually, I'll look on over your shoulder to see how it looks. Yeah, so go ahead and enter your name, not a nickname.
Okay.
Are you able to access everything?
Yeah, I just put in my name.
Oh,
It's
great.
loading.
Okay, sweet. Yeah, okay.
Oh, okay.
Just in case you were working on the survey, I switched the slide and this new QR code is the quiz for the course. Kindly write your own name instead of a nickname so that I can tell at the back end what's going on. Hope it's not too loud.
It's programmatic.
What's up?
Is it programmatic?
Programmatically, sorry. Yeah, I missed it. It means by code. Yeah. Passing is 7 out of 10. There are 10 questions. Yeah.
that's not timed, right?
No, it's-
Let me know when you finish. If you just don't want to do it, that's fine too. Oh, with that,
No, okay, Google disagrees with you.
Google disagrees with you. Google the answer?
Yeah, it says I can train my own
No.
ChatGPT from scratch. And
No,
it
you
says
cannot.
You can't. No.
Does it really?
Look, see, yes, you can train ChatGPT.
No, that's wrong. Is it generated by an AI?
Change your
What's the
answer.
link?
See, even gives me how to do it.
No, it's totally, no, that's totally wrong.
Oh,
Yeah.
right.
Yeah, you can feel free to Google, there's,
You disagree with Google. What's the point?
that's just wrong. You're done?
This one's right.
Oh.
It's number 2.
Just to number 2. So it's 4:02. We can go with this until like 4:10, 4:15. Yeah. 4:15 then. Okay. 4:15, and then we will continue with the last slide. So no rush, take your time. As you're doing it, just note, I will be sending this homework later on. You'll get an email with it, but it contains a small programming assignment from day 2. So if you're taking it for a grade, then it's paramount that you do submit it and the quiz. But if you're not, it'll be, I can definitely check your code and see if things look good. I'll send out an email later. I think if it tells you that you're done, I have not used this tool before, but yeah, it's. Oh, I should be able to see it on my end, so there shouldn't be a problem. Okay. Some people have already submitted. Okay, who's done? Done. Working on it.
I'll just submit it. I just finished all.
If it gives you a podium rank, I think you're done.
Oh, okay.
Yeah.
Oh, yeah, I don't think there's a submit button, but it's just like I finished all the questions.
Okay.
and it's
I
like,
guess I actually go back.
Okay, okay.
We can restart in about 4 or 5 minutes.
What is ground truth?
Label data, as we discussed in the first day. Yeah. Data, data with labels. Usually human annotated. We will start in 2 to 3 minutes. I was going to set a 20-second timer for question. In retrospect, not doing that would have been, yeah, it was a good idea. Because that's the default in Kahoots. I don't know if you know that. Yeah. Yeah, it's 20 seconds. Yeah, you only have so much time. Yeah, yeah. Okay, shall we proceed? Okay, so we're nearly done. So the outcomes of your workshop so far was that you can explain, at least to a rough extent, the underlying principles of LLM architectures, describe some of the strengths and limitations, and maybe at least at the bare bones, assess the feasibility and the challenges of incorporating them in your own workflows. And I think you have had a very like holding your feet to the fire kind of introduction to Python and using transformer models, LLMs in Python, which is I think the main focus of this workshop. What you cannot do is you still cannot train your own models. I think you're very nearly there, but you're not quite there yet. Also explain to a more accurate level how, for example, attention is done in the internal mechanics of the model. Of course, if you want to learn more about these models, you can refer to any of these courses. I'm sure there are more in statistics and math that will give you more information about transformer models. You can also consider working with our group. That's our PI's website. Okay, with that, I think we've reached the end. If you want to take a photo, you can take a photo. But okay, that's pretty much my last slide. Thanks. And Eloy, I think we're done here. What's up? Yeah, you can do it. There's no time limit.